Hello and welcome to the course of Advanced Algorithm Analysis. In this week, we will study important concepts related to another a very useful data structure which is known as graph. Let us start our lecture with a brief overview of the outlines. We will start this lecture by highlighting the objectives. After that, I will talk about a very historical problem which is known as the Seven Bridges of Konigsberg. After that, I will introduce you to the concept of graph, different terminologies, and different types of graphs. And then we will see how we can represent a graph inside the computer memory. There are two different methods. We will shed some light over them. Moving forward, we will talk about the applications of a graph, different areas where graphs can be used. And then at the end of this lecture, we will see two very useful methods for traversing of a graph, and they are known as BFS and DFS. Let us see the objectives of today's lecture. At the end of this lecture, the students will be able to learn the basic concepts of a graph theory, different terminologies, and different types of the graphs. Besides, you will be able to learn about the application areas where graphs are playing an important role. Similarly, you will learn about the representation of the graph inside computer memory. And beside, you will also learn about traversing of a graph. More specifically, we will be talking about two different types of methods that are available to visit each and every node of a graph. And they are known as breadth first search technique and depth first search technique. Let us start with the seven bridges of Konigsberg. It is a historical problem in mathematics. Konigsberg was the name of a city in Prussia. It's still there, but the name has been changed. The current name, if I am not wrong, is Kaliningrad. It's in Russia. Actually, the problem is like this. Uh, there is a river, as you can see here. The name of the river was Prigel River or Prigel River. It divided the city of Konigsberg in four lands. Land number 1, land number 2, land number 3, and land number 4. This is our river. What you see in the yellow color, they represent bridges. You can say that these four pieces of lands were connected by 7 different bridges. Let me repeat. The river has 4 land areas, and these land areas are connected with the help of 7 bridges. Now the Konigsberg problem is like this. Starting at any one land area, is it possible to walk across all the bridges, for example, like this? Okay, crossing uh, cross all the bridges exactly once and return to the starting land area. Let's suppose I start from land area number 1. So is it possible to visit all these bridges or goes through all these bridges exactly once and then return to the same lane from where we started? So we started from lane number 1. Let us give it a try to solve the problem. I start from here. I visited this lane. Okay, I visited second lane. Now I want to visit third lane, and then I want to visit fourth lane. I'm done. Now what I need to do, I need to return to the starting point, which is 1. But the condition is that I'm not allowed to go through the same bridge that I have traveled once. Let me see. Okay. Okay. And I stuck here because there is no way to go back. If I go back using this route, then I have already traveled through this bridge and I am not allowed to pass through the same bridge again. Okay, so the problem is like this. Starting at any one laned area, is it possible to walk across all the bridges, okay? So in this case, I have missed to pass through these two bridges and do not fulfill the criteria. To answer this question, actually it is not possible to solve this problem. And then at that time, this question was given to a famous mathematician known as Euler. Euler proved that the problem has no solution. But in 1730s, the concept introduced the foundation of the graph theory. Okay, so the problem was unsolvable, but it leads to another very interesting theory, and that is known as the graph theory. Euler is, you can say, he's like the father of the graphs theory. He worked a lot. He was actually a mathematician, but he worked on the theory of graph, and the concept arrived from the 7 bridges of Konigsberg. To solve the problem, Euler pointed out that the choice of route inside each lane is irrelevant. What is important is the sequence of bridges that once crossed, because this will allow him or her to reformulate the problem in an abstract level. So this was the original problem. He think on the problem, and then he come to the conclusion that the lanes can be represented by different nodes. So we have 4 nodes. 4 lanes mean 4 nodes actually, and the lines connecting the nodes, which are bridges here, Euler called them links. So we have 4 lanes areas, which means 4 nodes, and then 7 bridges, which means 7 edges, which are connecting these nodes. And this resulting mathematical structure is known as a graph. Now let us see the introduction of a graph. This was historical background from where the concept of the graph was actually derived. We have 2 types of data structure. One is known as linear data structure, and the second one is known as a non-linear data structure. Data structures like array, stack, queue, linked list, etc. are examples of a linear data structure. On the other hand, data structures like tree and graph are commonly referred as a non-linear data structure. Why? Because the elements are represented in the form of a hierarchy, in the form of levels. You can say the graph is a non-linear data structure which consists of 2 things. First thing is set of vertices, which is also known as nodes. And the second thing is set of edges, which is also commonly referred as links. And what is the role of this link? It will actually combine or join a pair of vertices. You can see here we have 2 nodes, 1 and 2, and it has been linked with the help of an edge, right? So we have a pair of vertices or nodes 1 and 2, and it is linked with the help of a link, and the combination of it is known as a graph. These edges or these links actually represent paths, or you can say connections between the vertices. Another formal definition of a graph is like this. For example, we have a graph which is represented by G. It is actually a set of two things: vertices or nodes, and edges are links. So you can say that a graph G is a set consists of a set of vertices, which is also known as nodes or sometimes points, and it is represented by V, and a set of edges, which is represented by E and commonly referred as links, such that each edge in this set, or you can say each link in this graph, is a connection between a pair of vertices in V. And it is clear from this graph, every link, every edge is actually a connection between a pair of vertices. How many vertices do we have here, or how many nodes do we have here in this graph? Actually, we have, you can count them, 1 2 3 4 5 nodes, and total number of vertices here 1 2 3 4 5. They are also 5. It's not necessary that they always have to be the same. They could be different. Even you can have more than one path possible between any two a set of vertices. Okay, so this is a proper definition of a graph, and visually we can represent vertices as points or a labeled circle, and the edges, they are represented as lines, but they must have to join the vertices. And this figure is actually a proper representation of a graph. Here the graph has 5 vertices, and they are labeled from 1 to 5, and also they have 5 different edges represented by lines. Some concepts which are related with the graph, we are going to elaborate them. The first concept is the path. We studied about the nodes and the edges. Now let us see the path. In a very simple way, you have a starting point which is known as a source, and you have an ending node which is known as a destination. In this case, our source is 1 and destination is 4. Suppose we want to reach to the destination. Different options are available. You can reach to 4 by following this path. I use the word path. Okay. First, I need to go to the node number 2, and then from there, I can actually reach to 4. This is one path. Second possible path is to first move to node number 3, then node number 2, and then node number 4. This is our second path. So I'm sure you know the concept what a path is. Let us elaborate more the concept of a path. A path in a graph is the sequence of vertices. Sequence of vertices, such that from each of its vertices there is an edge, a link to the next vertex in the sequence. As we saw here, we want to go to node number 4, which is our destination. So actually this path in the graph is a sequence of vertices. First node in this sequence is 2, and the second node in this sequence is 4. Actually, it is a sequence of vertices. The condition is that each of its vertices, let's suppose 1 to 2, there must be an edge to the next vertex. Here, the next node is 2, and we have a link here. The next vertex here is 4, and we have a link here. Suppose you want to come to 4, which is our destination, but by following this route. Is it possible? No. Why? We have a sequence of nodes. Okay, that condition is met, but we do not have a link between these pair of nodes. As we do not have any link between these two nodes, so it is not a valid path. So the definition of a path is actually highlighting two things: sequence of nodes and a link or connection or an edge must be there to the next vertex in the sequence. An important property of a path is that, as we know, a sequence of vertex, but the property is that each vertex in the sequence must be adjacent to the vertex next to it. Here we can see different paths. We have a complicated graph here. The nodes are labeled by using ABC, and the links are represented by straight lines. We have a path. Suppose we want to start from node A. This is our source, and our destination is, let's suppose, G. This is our destination. Okay, this is our source. Here is a path. From A, I can move to node E. They are adjacent. There is a link between these two nodes. And then from E, I move towards K. From K, I move towards P. From P, I move to L, then Q, then M, H, D, C, and finally I reach to my destination. This is an example of a path. The red lines are actually representing a path from source to destination. You can see this is a sequence of nodes, and every pair of the node is connected by a link. This type of path is known as simple path. And the definition of a simple path is very simple as well. If a path has no repeated vertex, then it is known as a simple path. Okay, any path which do not have a repeated vertex, or you can say a repeated node, it is known as a simple path. And this is an example of a simple path. Let us consider another thing, a closed path. Okay, suppose our source here is A and our destination here is B. Once you decide to go to the destination, which is B, then you have to traverse like this. Go to the E, which is the adjacent vertex in this graph, and then from there move back to B. So when you move back from B to A, then it is a closed path. Here one node is missing, and there is A in this equation or in this example. The correct sequence is like this: A, E, B, and then A. What do we mean by closed path? Means the starting and the ending node or vertex is same. So you move to E, then to B, and then back to A. This is an example of a closed path. Another concept related to the path is not a path, and we saw it in the definition. If you want to move from source to destination, your source is B and your destination is D, and you want to follow this route, B to C and C to D. That is not possible because we do not have a path, direct path between B to C. You, you can say that there is no direct path available between B and C. So you cannot traverse or reach to D by following C, although there are other options available. For example, you can go this way, or you may go this way, and other alternatives are available. But in this particular case, for this particular case, that is not possible. Another concept is a non-simple path. Simple path, we just define that any path in which there is no repeated nodes or no repeated vertex. On the other side, if we have a repeated vertex, then it is known as a non-simple path. And the example is here. Suppose our source is A and our destination, the point, the node where we want to reach out is L. And the sequence of nodes that we follow is mentioned here. From A, move to B. From B, move to E. From E, move to F. From F, move to G. From G, move back to B, and then again to G, and then to I. Or is it I or L? L. L. So you see, we have visited G twice. We have visited B twice. Repeated vertices are there, and this is known as a non-simple path. Final concept is known as length of a path, and that is simple. The total number of edges in that path moving from source toward destination is known as the length of a path. How many edges you traverse, you take to reach to the destination will actually give you the length of that path. Suppose you have a bus which started at station A, and then it take a stop at station E, another stop at K, another stop at P, and so on. So you can count these stations, these bus stops, to be the length of the path. In this particular example, suppose our source is A and our destination is G, and the total number of nodes, or the total number of edges actually that we visited. You count them like 1, 2, 3, 4, 5, 6, 7, 8, 9, and finally 10 to reach to the destination. In this case, the length of this particular path is 10. Next concept is called a cycle. A cycle is a term which is related with the path. So you can say a cycle is actually a path such that it meets the condition. What is the condition? The starting vertex and the ending vertex are the same. Yeah, we can say it is a cycle, as we just saw in the example of the closed path. The cycle is the same thing. If there is a path such that the starting vertex and the ending vertex are the same, or you can say a path which begins and end at the same node is referred to a cycle. And then we have a simple cycle and not simple cycle. A simple cycle is a cycle which has no repeated vertices. On the other hand, if there are repeated vertex, then there is an example of a non-simple cycle. And here is an example of a cycle which is mentioned here. For example, we started at node K. This is our source. We start at node K. And then from here, we move. Let's suppose we move toward J, then toward K, then toward N, and from here back to K. Then from here, we move to P, and then to O, and then back to K. So this is a cycle. We start and end at the same node. But you see, we have visited a particular a particular vertex, there is k more than once. In this case, it is known as a not simple cycle. On the other hand, if you see another example, which is the case of a simple cycle, you can see it in the graph as well. Think on the graph and find out what is the simple cycle here. First, compare this graph with the previous one. It is almost the same. So let us start from A. Our source is A, and suppose our destination is also A. The red lines will give you the path. First visit node E, then K, and P, L, Q, M, H, D, C, G, B, and finally A. We have started from a node and we have ended on the same node. This is a cycle, but a simple cycle, because you can see in the path we do not visit any node twice, more than once, repeatedly. Every node was visited exactly once. So this is an example of a simple cycle. Now let us move toward another concept which is known as a subgraph. As the name indicate, a subgraph is actually a subtype which is also a graph. Two things about subgraph: it will be a graph in itself, and the second property is that its edges and vertices are subset of the main graph G. Simple. You are deriving a graph from another graph. So the graph that you have derived, it must be a graph itself. And the second thing is it must be a subset because it has been derived from the graph G. So suppose our subgraph is H and our main graph is G. H is said to be a subgraph of G if it is itself a graph and the vertices and edges are a subset of the main graph G. So if these two properties meet, you can say that it is actually a subgraph of the main graph G. And here is an example. Suppose the vertices of the uh, first let us see what is the subgraph here. The subgraph here is shown by the red lines. This is actually our subgraph, more or less like this, the red lines. What are the vertices of this subgraph? If I talk alphabetically, they are B, then we have D, E, F, G, H, L, P, and Q. And what are the links? So the links are here. We have a link from B to E, the first link. We have a link from B to G. We have a link from E to F. Similarly, we have a link from D to H. We have a link from L to P. And finally, we have a link from L to Q. Now, this is an example of a subgraph because it is a graph itself and it has all the nodes are actually a subset of the main graph G. Another concept is degree of a node, and you know about this term from the tree concepts. We have studied about it already. What is degree? Degree is actually you can say the number of links or connection that a node has to other nodes in the network. In other words, you can say that the degree of a vertex V represented by V, a graph represented by G, and it can be written like this: dig of V, mean degree of V, is actually the number of edges, the number of links, the number of connections in this graph incident on a vertex V. If the definition is a bit tricky, let us see an example. We have a graph here. The nodes are labeled from A to E. Total number of nodes here are 5. and total number of edges here 1 2 3 4 5 6 7. Now we are asked to find the degree of the node B. Actually, the total number of lines leaving or entering to B is the degree. So 1, 2. In this case, the degree of node B is 2. What about the degree of node C? Same formula, same concept, same technique. Total number of lines 1, 2, 3, and 4. The degree here is 4. Same is the case with E. Count the number of lines 1, 2, and 3. Or here the degree is 3. So the degree of node E is 3. One thing you might be thinking is that this degree does not give us complete information. Later on, we will see that there are different types of graph, like directed and undirected. It is not clear whether these lines are ending at B or they are initiated at B. It's not clear. We have another concept which is known as out degree and in degree, and that is related with the directed graph. And we will see in a couple of slides that what is actually a directed graph and what is undirected graph. For the time being, if the line has arrows, then it is an example of a directed graph. It actually see the directions, and it is clear to you from here that now it is possible to say whether the line is initiating at a node or it is ending at a node. So we have two related concepts here, out degree and in degree of a node, and that is simple, like the degree of a node. The total number of edges beginning from a node is called the out degree, and it is represented by out dig v. In a similar way, the total number of edges ending at a node is called the in degree, and it is represented by in dig v. Let us see an example. In this case, in this graph, the node B has a degree. The total degree here is 2, total number of lines, either initiating or ending at B. But if somebody asks you what is the out degree of B, how many lines are actually out degree? How many lines are actually beginning or starting at B? So we have only one line which actually started at B. The out degree of B is 1. Similarly, the in degree of B is also 1. How many lines are actually ending at B? Only one line ends at B. In this case, the out degree is 1 and the in degree is also 1. Now consider the case of node A. What is the out degree of this node? How many lines are actually starting at A? We see 3 lines. So the out degree of A is 3. And what is the in degree of A? The in degree is 0 because we have no line ending at A. Same is the case with E. The in degree is 3 because 3 lines are ending at E. But the out degree of E is 0. We have no line which is starting at E. This is the concept of in degree and out degree of a graph. Let us see some types of the graphs. There is a very famous category of graphs which is known as a complete graph. A graph, let us say G, is said to be a complete graph if there is a path. Remember path, the definition of path is different from the link, from the edge. When there is a path, we are talking about a source node and a destination node and the number of and the sequence of nodes that we are taking to reach to the destination. There is a path. So a graph is said to be a complete if there is a path from every vertex to every other vertex. Let us see some example. In this case, we have only 2 vertices. For example, 1 and 2, and they are connected. There is a path between these 2 vertices, so it is an example of a complete graph. Second example, we have three vertices, 1, 2, 3, and there is a path from 1 to 2, there is a path from 1 to 3, and there is a path from 2 to 3. Or there is a path from 1 to 3, and there is a path from 3 to 2, and there is a path from 2 to 3, etc. This is also an example of a complete graph. What about this one? We have 4 vertices now. 1, 2, 3, 4. Suppose you want to reach to all the nodes from this node. If that is possible, then it is an example of a complete graph. Okay, that is possible, and that is possible. Now consider 2. We have a path, here, and also we have a path here. Or you can take alternative path as well. Same is the case for other nodes and for these examples as well. In simple word, a graph is complete if there is a path from every vertex to every other vertex. Consider this mesh topology, this graph, and consider this is our source and this is our destination. Is there a path available between these two vertices? Let us see. Yeah, actually we have more than one paths available, but at least one path must be there between any two vertices. If that is possible, if that is true, then we can say this is a complete graph. Complete graph are also known as fully connected graph or strongly connected graph. These are the other names to refer to the complete graphs. And two of the very famous graph types are undirected graphs and directed graph. Undirected graph, very simple concept, where edges has no directions. What is edges? The lines, the links, the connections between any two nodes. They have no direction. If they have no direction, then it is known as undirected graph. There is a property of undirected graph, and that is in undirected graph, the edge between any two vertex, suppose A and B, it must be identical. Means the edge from A to B is identical to the edge from B to A. Okay, if you move this way or this way, let's suppose the cost is equal. So in case of undirected graph, if there is a link which is connecting two nodes, then it is identical either from A to B or from B to B. It is the same thing. An undirected graph can be represented geometrically as a set of points or nodes, as we know, and they are connected with the help of lines, but the line have no direction, no arrow points. And here is an example of undirected graph. As you can see, the nodes are connected by lines which have no directions. On the other side, a directed graph is actually a graph which has directions. And this is a special type of graph, by the way, which is sometimes known as digraph as well. This is the second name to refer to a directed graph. And it can be written as D, which stands for directed, V stand for the vertices, and A stand for the ordered pairs of vertex. Actually, V is the set whose elements are called vertex or nodes, and A is a set of ordered pair of vertex, and it is known as edges, arrows, or simply arcs. A for arcs. Suppose we have an arc like this, A for arc, and it is an ordered pair of vertex, mean two vertex. X is a vertex and Y is a vertex, or nodes. Then it is considered to be directed from X to Y. Means the line now has an arrow which starts at X and which ends at Y. So an arc, a line A equal to XY means that it is directed from X to Y. In this case, y is known as the successor of x and x is known as the predecessor of y. Means come before y and y means come after x. Let me repeat. If we have an arc from x to y, it means that the direction is from x to y towards y, or it starts with x and it ends at y. In this case, the y is referred as the successor of x and x is referred as the predecessor of y. And again, it can be represented diagrammatically, geometrically like this. The nodes are inside the circle, which are also known as vertex. And we have a set of arrows called edges between every pair of vertex. So there is at most one arrow from one vertex to another. And you can see we have a line, an arc, which start at A and ends at B. And similarly, we have an arc from A to D. And we also have an arc from D to D. This is a special condition and we will come to it later. Now we have to represent two things. We need to identify two things: the vertices, which is A, B, C, and D, and the edges. Now it has direction. It is more clear. We have an edge from A to B, an edge from A to D. We have an edge from D to D, and we have an edge from D to B. And finally, we have an edge from C to C. The vertex A in this particular case is called the initial vertex, and B in this case is called the terminal vertex. But for the edge AB, for this particular line, as I just explained here, this A is known as the initial vertex and this B is known as the terminal vertex of the edge A and B. If an edge there is incident from end into the same vertex, just like this, the starting and the ending point of the vertex, if it is the same, for example in this case or in this case, such situation is known as a loop in the graph terminologies. Let me repeat: if an edge start and end at the same vertex, then it is known as a loop. And another concept is the adjacent vertex. Two nodes are said to be adjacent to each other if they are joined by a link, by an arc, by an edge. Okay, so A B are adjacent, AD are adjacent, and BD are adjacent because they are joined by an arc directly. Okay, finally a concept here is that of the isolated vertex. If there is no edge starting with it, which leads to another vertex, then it is known as isolated vertex. And in this case, C is an example of isolated vertex. Sometime, oops, this slide is repeated, ignore it. Sometimes we have another component, a third component. Two things we have studied: vertex and edges. Now we have a third component, and that is associated with the edge. It is known as cost or weight, and it is used to measure the cost of traversing that edge. Now this leads us to the concept of weighted graph, another type of graph. You see, now we have a third component. We have a number associated or linked with every line, with every link, with every edge. If you see a number associated with each link, then such type of graph is known as weighted graph. Weighted graph. A graph which has a weight or a number associated with each edge, link, line, connection is known as a weighted graph. Very simple. If you have a number, if you see a number with every line, then it is known as a weighted graph. The question is, what is the weight about? Sometimes this weight is known as a cost. So it is about cost. Again, cost of what? Actually, this weight represents certain conditions or situations associated with the edge. It could be distance, it could be speed, etc. Suppose you have two cities N and M, and you want to travel from N to M. N for New Delhi, M for Mumbai. Then this 47 means the distance in kilometer. For example, for traveling from N to N, the distance is 47. Or it could be the time in minutes. If you are traveling at a constant speed, for example 120 km per hour, then you will be able to reach to the Mumbai in 47 minutes. Although it depends on the traffic condition, but we are trying to ignore them to make the thing simple. So the number could represent anything. But if the number is associated, then such type of graph is referred to as weighted graph. And finally, let us see. Oops, some slides are repeated again and again. Sorry for that. Finally, we have connected and disconnected graphs. Any graph is said to be connected if there exists at least one path, at least one path, that is important, between every pair of vertex. Okay, and we are talking about undirected graph where we have no directions. So a graph is said to be connected if there is at least one path between every pair of vertex. Pair of vertex, you are quite familiar with it. For example, our pair of vertex is A and C. So there is at least one path here. Suppose our pair of vertex are A and B. There is at least one path here. Suppose our pair of vertex is A and D, for example. Oh, we have at least one path here as well. This is an example of connected graph. On the other side, we have a disconnected graph, and that is opposite. A graph is said to be disconnected if at least two vertices of the graphs are not connected by a path. And we have two vertices here, and they are not connected. A is not connected to C. You see, you cannot go like this, you cannot go like this. And same is the case with B and D. They are not connected with one another. So this is an example of a disconnected graph. So a graph is disconnected if at least two vertices of the graph are not connected by a path. And if it is an undirected graph, as in our case, that is said to be disconnected if there does not exist at least one path from any vertex to any other vertex, like from B to D or like from A to C. We do not have any path. Similarly, between B and C, we do not have any path. And between A and D, we do not have any path. So it is more than one vertex. They are not connected with one another. They have no paths available. And such of the graph are known as disconnected graph. Okay, now after discussing different types of graphs, different terminologies, let us turn our attention to the representation of the graphs in computer memory. There are two standard ways of maintaining a graph in the memory of computer. The first method is known as adjacency metric, while the second method is known as adjacency list. First, we will explore the concept of matrix, and then we will explore the concept of adjacency list to represent the graphs in computer memory. They are very simple methods, by the way. I hope you will understand them very easily. The first and most common and simple representation of a graph is the adjacency metric method. In this method, actually metric is a square and you know about it. You have learned two-dimensional array or multi-dimensional list in Python, etc. So you are quite familiar with the matrix, the concept of the matrix. It is actually a two-dimensional array When we talk about two-dimensional, we mean something which has a row and something which has columns. And as we are talking about graphs, so we are talking about vertex and the edges. Okay. In this two-dimensional array, which consists of rows and columns, suppose the row is represented by I and the column is represented by J, then we have to put entries. Let's suppose your two-dimensional array or matrix is like this. I will represent the rows and column will represent the J. And then you have to put entries in these cells, either 0 or 1. 1 will mean there is an edge between two vertices, and 0 will mean there is no edge between two vertices. Okay? And this is actually defined here, 1, if there is an edge from any vertex I to any vertex J. Ij could be 1, 2, A, B, anything. And otherwise we have to put 0 if there is no edge between the vertex. We will see examples, and I'm sure this concept will clear with the help of example. But the theoretical part is that we have to represent a graph by using two-dimensional array or matrix, and the values in the matrix are either 0 or 1. 0 if there is no edge between two vertex, and 1 if there is an edge available between two vertex. And this is for the undirected graph, by the way. But we can also represent a directed graph by using this method. We will see them in a moment. What is the rule for a directed graph and also a weighted graph? Weighted mean a number associated with each link. We will see how we can represent these different types of graphs with the help of a different example. Let us see examples. The graph is given to you and you are asked to represent this graph with the help of adjacency metric method. These are the nodes of the graph. We have 5 nodes, and the lines are actually the links, the edges. And this graph is an example of a directed graph. You can see from the arrows. The method is simple: total number of rows and total number of columns. How many nodes do we have here? 5. So 5 by 5 metric. And I will represent like the rows and J represent the columns. Let us see. These are the numbers of the nodes. Okay. We have node 1. Is there any link, any edge from 1 to 1 like this? No, it's not there, so we have put a 0. Is there any line starting at 1 and ending at 2? Yes, we do have a line here. So the entry here is 1. Is there any line, any link from 1 to 3? This is 1, this is 3. Yes, we do have a line here. The output is 1. Do we have any link from 1 to 4? Direct link from 1 to 4? Yes, we have a line, but the direction is opposite. It starts with 4 and end at 1. If we do have a line like this, okay, we can put 1 here. But now we cannot put 1 here. We do not have a line from 1 to 4, starting at 1 and ending at 4. That is why the value here is 0. And same is the case with 5. Do we have any line starting at 1 and ending at 5? No. We have put 0 here. And same for other values. Now we consider node 2. Do we have a line which start at 2 and end at 1? No. So the value is 0. Do we have a loop like this? No. The value is 0. Do we have a line from 2, a connection, an edge from 2 to 3? No. From 2 to 4? No. From 2 to 5? Yes, we do have. The output is 1. And you can fill the rest of the values. For example, let us see 5. In case of 5, the only line is 5, from 5 to 5. So we have 1 here, and rest of the values are 0. If this example is not clear or you have any confusion, let us consider a second example. Now the graph given to us is has no direction, undirected graph. Okay, we have 5 nodes, so number of rows, number of columns, 5 by 5 matrix, and rest of the concept is same. If there is an edge from 1 to 1, then the value will be 1, otherwise 0. We do not have it, therefore the value is 0. We have a line from 1 to 2, so the output is 1. We have a line from 1 to 3, so the output is 1. We have a line which connect 1 with 4, the output is 1. We do not have a line which connect 1 with 5, so the output is 0. The only difference between this directed and this undirected graph is that here you have to consider this line for both. Like this line is for from 8 to 2, from 1 to 2, and this line is also from 2 to 1. You can see the value here is 1 because this is identical line from A to B, and from 1 to 2 and from 2 to 1 as well. And you can put rest of the values by yourself. These are some more examples. Actually, we have 3 graphs and their representations are here. Let us consider this first graph, G1. How many nodes do we have here? 4. So first you have to decide on the matrix, that is 4 by 4 matrix, and then you have to write the name of the nodes like A, B, C, D and I, B, C, D, and then see whether we have a line which connect two vertex or not. A to A is 0. We do not have any line, or you can say loop here. Then we have a line from A to B and from A to D, from A to B and A to D. We do not have any line from A to C, so value here is 0. Now consider node B. Do we have a loop? No. No loop is here, so the value is 0. Do we have a line from B to A? Yes, we do have. Do we have a line from B to C? Yes, we do have. Do we have a line from B to D? No. So the output is 0. Consider C. We have a loop? No. So the output is 0. From C to C, we do not have any line. But we do have a line from C to D and from C to B. C to B and C to D. And we do not have a line from C to A. So the output is 0. And you can try the other examples by yourself. Lastly, sometimes we do have a number associated with the lines, or you can say a cost associated with the lines. You can also represent this type of graph, or you can say weighted graph, with the help of adjacency metric method. The only thing is that you have to write the cost of the link instead of 1. In the previous example, we write 0 and 1. Here you have to write the cost, actual cost. And also sometime the given cost is 0, although logically is not true. But if you have a cost which is 0, then in that case you will get a problem, and the problem is whether this 0 is the cost, or this 0 means that there is a no connection between the two nodes. To get rid of this situation, we actually replace 0 with -1. -1 means there is no connection between two vertices. Okay, and 0 means the actual cost. Let us see. Consider node 1. Do we have a line from 1 to 1? So no mean -1. Mean there is no line. Do we have a line from 1 to 2? Yes, we do have a connection from 1 to 2. What is the cost? So you have to write the cost, not 1. You see, I have write 5 here. That is the cost of the link from 1 to 2. Moving forward, let us see. Do we have a link from 1 to 3? Yes, we do have. What is the cost of that link? 3. Just write the cost of the link. 4. This is actually 4, node number. Do we have a line, a link between 1 and 4? No, we do not have. So we have to put -1. And now 5. Do we have a line from 1 to 5? No. -1. Now consider node 2. Do we have a line from 2 to 1? No, we do not have. The value is -1. Do we have a line from 2 to 2, a cycle? No, we do not. Output is -1. Do we have a line from 2 to 3? No, we do not. From 2 to 4? No, we do not have. This is 4. -1. Do we have a line from 2 to 5? Yes, we do have. And what is the cost? 7. So just write the cost of the line from 2 to 5. And same is the case with other nodes. Some more examples you try by yourself to get more practice. Now, second method. Our second method of representation of the graph inside computer memory is known as adjacency list, or you can say linked list representation. Here, the theoretical part is like this. Suppose we have an array represented by A, and the total length, the total element in this array is represented by n. And you know each entry in this array is ai. I is the index. It could be 0, 1, 2, 3. Actually, it contains a pointer to a linked list where the values of the nodes are stored. The pointer will be saved at this location. Actually, you can represent, like as we saw, undirected graph, directed graph, as well as weighted graph by using the adjacency list representation. To see how it works, let us see an example. Actually, this is the array and this is the list, and these are the indexes, the pointers, which actually refer to the node value stored in the list. But the question is how it works. Let us see how many elements, how many nodes do we have here. 1, 2, 3, and 4. Just write them in the array. Okay, now the adjacency list for a vertex, for example 1, is actually the list of all vertex adjacent to it. Adjacent means directly connected. You can see 1 is directly connected with 3 and 1 is directly connected with 4 as well. These two are the adjacent vertex of node 1, 3 and 4. Now you have to connect them with this one. First I write 3 and then 4, just to be to write them in a sequence. You can write 4 before 3, it doesn't matter, because both of them are adjacent to the node 1. If you want to access this node, first you have to go to the array, find it index, and then by using that index you can actually refer to this node. And if you remember the concept of linked list from data structure, we know that a list, any node of the list, any item, any element of the list actually is made of two parts if it is a one-dimensional list: element and pointer to the next variable. This list will contain an element, that is 3, and also a pointer, an address of the next node, next element in the list, that is 4. And overall it means that with this node 1 we have access to these two nodes because they are adjacent to 1. Now let us see the case of node number 2. What are the adjacent nodes to node B, to vertex B? There is only one node, and that is 4. Okay, so 2 is actually, sorry, again this is misprinting, 4. Make the correction. 2 is connected with 4. Now let us consider the next node, that is 3. It has a connection with node 1 and node 4. So you can see here 1 and 4. And finally node number 4 has connection with node 1, with node number 2 and node number 3. You see 1, 2, and 3. This is the linked list representation of the graph, and it is with the help of a linear array. The size of this array is n, which means total number of nodes. In this case, there is 4. Okay, and every element of this array will contain a pointer. These are the pointers, not the node element, not the actual values. These are actually the pointers. So the pointer to the linked list, and the linked list will contain the neighbors of this vertex I. You can say that the adjacency list for a vertex I is a list of all vertices that are adjacent to it. In our case, adjacent to A are 3 and 4, adjacent to 2 are only 4, adjacent to 3 are 1 and 4, and adjacent to 4 are 1, 2, and 3, and they are being represented here. Let us see another example to clarify the things. Now we have a directed graph. The concept is same, the technique is same. Only we are dealing with a directed graph now. Okay. Again, we have an array. How many nodes do we have here? 4 nodes. 1, 2, 3, 4. What are the adjacent node of A? Oh, 2, 3, and 4. So you can see 2, 3, and 4. Actually, this is the last element. So in the last element, the pointer field is empty. It does not contain address of the next element because we do not have next element. Okay. And next we have the node 2. It is actually it has only one adjacent node. There is 3. So you can see it from the list. And then 3 has only one node adjacent. There is 4. And finally 4 also has a single node adjacent. There is 3. See another example here. Okay, now this is about weighted directed graph, because we have a weight associated with each and every link. So if the graph is a weighted graph, a weight field can be added to the node structure. You see, now the linked list has contained, every element will contain 3 fields. Okay, in the previous case it contained 2 fields. See, 2 fields. Now it has 3 fields. Here each node has 3 fields. The first one is showing adjacent node. The second is showing the weight of that link or associated with the edge. And the third one is actually showing the link to the next node, as we saw in the previous cases. There is the link, this is the cost, and this is actually showing the node. Let us see. For the node number 1, the adjacent nodes are 2, 3, and 4. You can see 2, 3, and 4. The first part will contain the adjacent node. Here the adjacent node to 1 is 2. Here the adjacent node to 1 is 3. And here the adjacent node to 1 is 4. As we have a number associated with each of this line, each of this connection, second part will show this number. The cost from 1 to 2 is 5. The cost from 1 to 3 is 2. And the cost from 1 to 4 is 6. And here we will contain the address of the next node. Address of the next node. As this is the last node, so we do not have an address of the next field. This was for node number 1. Now node number 2. Only the adjacent node is 3 and the cost is 3. This is the node and this is the cost. Consider node 3 now. The only node is 4 and the cost is also 4. Consider 4 now. The only node is 3 and the cost here is 8. Okay, I'm sure it will be clear to you now how we can represent graph by using adjacency list. And this is the last example. Again, this is undirected graph, unweighted graph. How many nodes do we have here? 5. So the array is here. First, let us consider node number 1. The adjacent nodes are 2, 3, and 5. You can see 2, 3, and 5. Here we do have 2 parts. Every element, every node contains 2 parts. The adjacent nodes and pointer to the next element, pointer to the next element, and this is the last element. It does not have a pointer to the next element because we do not have next element here. Similarly is the case with the 2. Here we have only 2 adjacent nodes, 1 and 3. Now consider 3. We have, wow, here we have 1, 2, 3 and 4 adjacent nodes. You can see 1, 2, 4 and 5. 4 nodes are here, and then for 4 and for 5. This was the second method of representation of a graph inside computer memory. Now moving towards some applications of the graph in computer and in our daily life. There are plenty of applications available. Some of them are mentioned here. You can use the graph for transportation networks. And in this application, actually, the vertex are the intersections on the roads, and the edges are the road segments between them. Or you can say the vertex are the stops, bus stops, and the edges are the links between them. And this concept is used by many map programs, like you all are familiar with the Google Maps and the Bing Maps, and they are used to find the best routes between your location, source to destination, source to destination. So transportation network is the best example. You can use it for finding the shortest route, or maybe the fastest route where the congestion is less, or maybe the more safer route where there are no robberies and things like that, or where the road condition is good, like it does not have bumps and jumps and potholes, etc. Different applications are there. Another use of the graph, which is very common, is computer networks. Like a computer network actually consists of interconnected sites that sends, store, forward, and receive messages of various types. One use case is the IP addresses. You can consider them to be like the vertices of the graph, and the packets that flow between them are the edges. And different applications are available. You can actually analyze the network security by studying the spread of worms, viruses, and other security threats to the network. So it has its use in computer networks. And then social network. You can see the graph of your Facebook. It's a social app. Connections between your friends. Understanding the properties of social networks. It is possible, and different applications are available which will show you the graph of your Facebook. Who knows whom, who is connected to whom, who communicates with whom, etc. Similarly, another example is the Twitter graph. Who follows whom on the Twitter? These can be used to determine how information flows, how topics become hot, how communities are developed, and other things as well. In a similar way, we have a document link graph, and the best known example is the link graph of the web, where each web page is a vertex and each hyperlink is a directed edge. And link graphs are used to analyze relevance of web pages, to find the best sources of information and good link sites, etc. In a similar way, you can use graphs for semantic networks. Here, the vertex will represent words or concepts, and the edges will actually represent the relationship among these words or these concepts. Okay, so semantic network is there, which is an application of the graph. In a similar way, we can use graph for communication, like telephone sets or computers are the vertex, and the lines, fiber optics or wireless line connecting these devices, they are edges. For circuits, even in mechanical side, you can use graphs. For financial applications, you can use graph. Similarly, for internet, which is a network of networks, you can use graphs. For gaming purposes, social relationship, neural network, very in these days, where different neurons and synapses, the concepts are there, so you can represent them with the help of protein networks, chemical compounds, how they are formed, etc. Plenty of applications of the graphs are there, because the concept of the graph it has more than 200 years now. So it has plenty of applications in computer science and in other fields of science as well. Last week we studied about trees. A tree is actually a special case of a graph. You can say a tree is a directed acyclic graph. Any graph that is connected with no cycles. Remember the concept of the cycle we just explained? If a graph is fully connected and it does not contain any cycle, then it can be viewed as a tree. The question is that the tree has a root node. So you can pick any of its vertex to be the root of the tree. So that is possible. Now, after studying the application of the graph, our last topic for this week is how we can actually traverse a graph. Two methods are available. We will shed some light on the traversing of a graph. Traversing is basically an operation of data structure, which means visiting each node of a graph. Many applications of graph requires a structured system to examine, to visit the vertex and edges of a graph. So there is a graph traversal, which means visiting all the nodes of the graph. Traversing a graph means visiting each vertex. The simple traversal algorithms that we used for trees, like in order, pre-order, post order, they cannot be directly applied to the graphs. Why? Because graph may include or may contain cycles. So for this reason, the tree traversal algorithms would result in infinite loops. Another reason for not applying the tree traversal algorithms to graph is that sometimes graphs can have isolated vertex, as we saw an example, which means that some part of the graph are left behind. So if we use the tree traversal methods, these reasons or these properties of the graph will create problems. So we need specific methods for traversal of a graph, and two of the most commonly used method for graph traversal, they are known as breadth first traversal and depth first traversal. Although these two methods, depth first and breadth first, they are used for traversal, but they are commonly known as breadth first search instead of traversal and depth first search instead of traversal. They are commonly referred as the search operations on the graph or search algorithms, like the breadth first search and depth first search, or in short BFS and DFS algorithms. And these algorithms can be used to find out whether a node is reachable from a given node or not. Let us explain these two methods one by one. Our first method for the traversal of a graph is referred as breadth first search, or BFS in short. BFS provide us a systematic way of visiting all the vertices of the graph. As it is a traversing algorithm, so we have to visit all the vertices of a graph, and it will provide you a systematic way, means a proper way of visiting all the nodes. We cannot visit all the nodes randomly. We must have to follow some strategy. There is a systematic way. It is actually an algorithm for traversing, or even you can say searching, graph data structure. You may also apply them for tree because it is a special type of graph as well. How it works? In the BFS algorithm, we actually starts at the root if it is a tree. Or if it is a graph, then you can start the algorithm from any arbitrary selected node of a graph. And then after that, you have to explore all the neighbor nodes at the present level or depth before moving to the next node at the next level. Which means that in the BFS, we have to identify or pick any node of a graph, and then you have to apply the BFS algorithm on that node. After that, you have to explore all the neighbor nodes at the present level. Once you complete, explore, discover all the nodes at the present level, you can move to the next level and then the next level and so on. Let us see an example of the breadth first search algorithm technique. You can see from this example that it is like a level by level technique. We have a graph given to us, and we are asked to visit all the nodes traverse the graph with the help of BFS algorithm. In this case, first you have to select any node. For example, I have selected S. Once you selected a node, starting point, you have to apply the algorithm, which means we need to identify all its neighbor. So the directly connected neighbors are A, B, and C. After identifying all the neighbors at that level, now it's time to identify the neighbors at the next level. For example, this is our level number 0. We identify all the nodes at level 1, then move to level number 2. Here we will explore node D, node E, and node F. We do not have more nodes at this level, then you have to move to the next level. And on the next level, we have only a single node, that is G. So visit that node as well. Such technique is referred as BFS, or breadth first search algorithm. This was an abstract level example. Let us see a more detailed example of the breadth first search algorithm. Here we are actually using 3 different colors, which represent 3 different types of nodes. The white color actually represent not identified nodes. The light color will represent identified nodes, and the dark blue color will represent the visited. Our purpose is to visit all the nodes. We will start with an empty white colored graph, and then we will move gradually to visit all the nodes one by one. So here the first step is to select any node. Suppose to make the thing simple, I am interested to select 0 as my first node. So we start at vertex 0. Once you select it, you have to color it light. You can see the color of 0 is a light color. We visit 0, and after visiting 0, we see that 1 and 3 are the adjacent nodes 0. So we color them light. You see, 1 and 3. They are the adjacent nodes to 0. We identify them and we color them light, which means they are identified but not visited yet. Now we are finished with 0 because it does not have any other adjacent node. So color it dark, as you can see here, which means we have visited 0. Visited means we have identified all the adjacent nodes of this node 0. So far we have visited node 0 only. We always select the first node that was identified light color but not yet visited, and then we visit it next, which means you have two options, 1 and 3. They are identified but not visited yet. So you can select either 3 or 1, but to keep things simple, we have to follow the sequential order. So after 0, select 1. We visit 1 and look at its adjacent nodes now. Now this is your node that you have identified. You have colored it light, but it is not visited yet. So you have to identify its adjacent vertex. So the adjacent vertices of 1 are 0, 2, 4, 6, and 7. Okay, we skip 0 because it is not colored white, and color the other adjacent nodes to 1 as light blue. You see, this is adjacent to 1, adjacent to 1, adjacent to 1, and adjacent to 1. We color them light because they are adjacent to 1, and then we color 1 as dark. Now it means we have visited 1 as well, because we have visited it, which means we have identified all the adjacent nodes of 1. Then we have to look at 3 because it was the adjacent node of 0, second adjacent node of 0. Look at 3 and see that it adjacent vertices are 0 and 2. 0 have already been identified and been visited. So we are finished with 3 because 0 already done and 2 already identified. This is also an adjacent node of 1. So we are also done with 3. Mean 3 is visited. Why? Because it has two adjacent nodes, 0 already visited and 2 already identified. Okay, now we visited node 0, 1, and 3. We are finished with 3 as well. So until now we have visited node 0, node 1, and node 3, which are the starting vertex and all vertices adjacent to it. Now we visit 2. Remember, we are following a sequence. So the next node to visit is 2. And after visiting it, we come to know that the adjacent nodes are 3, 1, which are already colored. No need to visit them again. The adjacent nodes 8 and 9, which are white, so you need to color them light. Now they are adjacent to 2. Okay, so you can see here they are colored light, 8 and 9. And once we identified all its adjacent node, what we need to do, we have to color it blue, dark color. Now we have visited 2. Why? Because we have identified all the adjacent nodes. Then we have to visit node number 4. Okay, and here you can see that 1 is adjacent, 7 is adjacent, 6 is adjacent, and 5 is adjacent. So 1 is already visited, 7 and 6 already identified, only 5 is not identified. So we have identified 5 as well, which is adjacent to 8. So color it light. Yes, we have identified all the adjacent vertices of 4. It's time to give it the blue color as well. Okay, and you can see it in figure E. And finally, we have to visit node number 6 and 7, the last vertices that are 2 edges away from the starting vertex, and then 8 and 9, and also 5, and see that there are no unidentified vertices. So that is the final representation in figure F. The vertices have been visited in a sequence like 0, 1, 3, 2, 4, 6, 7, 8, 9, and 5. Actually, this technique, BFS algorithm, uses the concept of a queue, which is another useful data structure. For its internal implementation, you have to use a queue. How it works? let us see an animation. Internally, it uses a queue. Let us see an animation to explain the things in a more clear way. Suppose we have given a graph. The graph is shown here, and we are asked to apply the breadth first search algorithm on it. So as I just mentioned, we have to use a queue. This is what you see here is an example of a queue. And in queue, you know that we have two operations, in queue and dequeue. Whenever we add an item to the queue, it will be inserted at the back of the queue. And whenever we want to remove an element from the queue, it must be deleted or removed from the start of the queue. Let us start this animation. Give attention to the movement. First, we need to call the algorithm on any arbitrary node. Suppose the node that we have selected is A. Okay, we have selected A. We call the algorithm BFS on node A. Mark it and place it on the queue. Next, we have to identify all the adjacent nodes to A. Okay, so the adjacent nodes to A are, as we can see, they are C and E. The node that you identified, you have to place them on this queue. So first we identify C, we place it on the queue, and then we identified E and place them on the queue. After this, we are done because we have identified all the adjacent nodes of A. Now next step is to identify the adjacent nodes to C. Why C? You can see here. Okay, this is a queue. You have to remove the element which is at the front of this queue. So at the front we have C. Remove the C from this queue, which means apply the algorithm on the C, which means identify the elements which are adjacent to C. As you can see, the adjacent element are A, B, C, and E. A has already been visited, already been marked yellow, so we skipped it. Next adjacent element is B. Place it on the queue. As it is a queue, B must follow E. It must be placed after E. Next, the next element is C. We identified it and placed it on the queue. Next is E, but E has already marked, so we skipped it. We are done with C as well. We have identified all the adjacent elements to C. What we need to do, we have now to move to the next element, next identify element, that is E. Remove the okay, I forgot, F is also adjacent to C, so we have to identify it and place it on the queue. Next, we have to remove E from this queue. Okay, so remove the E and identify all the adjacent element of E. But you can see the adjacent elements are A, C, and F, and all have already been identified. Okay, so the algorithm will work, but it will not do anything. Next, after completing with E, we have to move to the next element, that is B. The top of the queue now has B. Come to B and see the adjacent elements. So the adjacent element here are C and F, and both are already been identified, so we will skip it. And then once we done processing with node B, we have to come to the next element, and that is D. Consider D. The adjacent nodes are C and F, but both are already been identified. So skip it, and then we are done with D as well. Now it's time to move to the last element of the queue, and that is F. Remove it from the queue, mean apply the algorithm on node F. The adjacent nodes are B, C, D, and E. But all are being identified, so it will be skipped. And that's it. This is the final BFS algorithm. So internally, we make use of a queue, and then we insert elements that we identified and then remove element one by one from the queue. This is how BFS actually works. Our second method for traversing of a graph is known as depth first search algorithm, or DFS in short. Like the previous algorithm, it also provides a systematic way to visit each and every vertex of a graph. It is also used for traversing or searching a tree or a graph data structure. Actually, here we have to use a technique which is known as backtracking. And we will see in the example how this backtracking actually works. We will explore the vertex by following down a path. As it is a depth first search technique, we need to explore the vertex by following down a path as much as possible. But then we have to backtrack by one vertex, continuing to follow paths from there and so on. In a similar way, this algorithm will start at the tree root node if it is a tree, or any other arbitrary node if it is a graph, and then it will explore as far as possible along each branch before backtracking. If the theory is not clear, let us see an example. For example, we have given a graph and we start with the arbitrary node which is marked as S. Okay, first we have to go as much in depth as possible. So as we are following sequence, let's select A. You can also select B or C as they are at the same level, but to follow the sequence, I have selected node A. And then go further deeper to the next level. There is D. After that, after visiting D, go further deeper. There is G. As this is the final level, then from here you have to identify its adjacent, which is D, already visited, E and F, and then E and F you have to select one, either E or F. So as we are following a sequence, I have selected E. After visiting E, I move one step ahead and visited B. As the adjacent node to B, which is S, has already been visited or identified, so I don't go there. From here you have to take a step back. This is called backtracking, backtracking, backtracking. And from here, take the next adjacent node, that is F. Once you reach here, identify the adjacent vertex. G already been identified, C missing, so visit it, that is 7. After visiting C, we saw that the adjacent node is F and S, both already identified, so it's time to go back. Backtrack, backtrack. From here, backtrack, and then backtrack, and then backtrack. So things are like this. To see a more detailed example of the depth first search algorithm, let us consider another example. We have given a graph. The first step to do is to select any arbitrary node. Suppose I have selected node 0. I have to apply the DFS algorithm on this node 0. We can start at any vertex, but for simplicity, we always start with 0. Now see the vertex that are adjacent to 0, and we know that the adjacent are 1, 2, 3, and 4. They are adjacent to 0. Once we identified the adjacent, we mark 0 as being visited. Remember this color, light color, being visited or being identified. Sorry, light color is being identified or being visited, and the dark color is finished visiting. So we have just identified 0. Next, you have plenty of options available like 1, 2, 3, and 4, but I have selected 1 again just to follow the sequence. So I have selected, I have considered 1 here, and then we mark 1 as being visited. Now the vertices which are adjacent to 1, they are 0, 3, and 4. Again, 0 is being visited. We mark 3 as visited, which is adjacent to 1. Okay, you can see in figure C that we have marked 3 as visited because it is adjacent to 1. The vertices adjacent to 3 now, they are 0, 1 and 4. As 0 and 1 are already being visited, we have to mark 4 as being visited, and that is clear in D. Now the vertices adjacent to 4, they are 0, 1 and 3, and all of these are being visited, so we mark 4 as finished. So depth first search, we started from 0 but we visited 4, which is the deepest first. Now we consider vertex 2. Okay, we have done with the one adjacent node. Now consider the next adjacent node to the 0, which is adjacent to 0 but has not been visited. We mark 2 as being visited, as you can see in figure F, but from here consider the vertices that are adjacent to 2. So the adjacent vertices are 0, 5 and 6. We mark 5 as being visited here, and consider the vertices adjacent to it. So adjacent to 5 are 2 and 6. 2 and 6 are already being visited, thus we mark 6 as finished. Okay, so here in H we mark it as finished. The vertices adjacent to 5 have all been visited, so therefore we mark 5 as finished. All the vertices now adjacent to 2 have been visited, so we mark 2 as finished as well. And finally we come backtrack to 0 because all of the vertices adjacent to it have also been visited, so we also mark 0 as finished, and we are done, and that is shown in figure I. The order in which we started to visit the vertices were like 0, 1, then 3, 4, and then 2, 5 and 6. But the order in which we finished visiting all the vertices were like 4, then 3, and then 1, and then 6, and then 5, then 2, and finally 0. So we started from the depth first. That is why it is known as the depth first search algorithm. The discovery order is actually the order in which the vertices are discovered. Okay, and the finish order is actually the order in which the vertices are finished. We consider a vertex to be finished when we return to it. Backtracking approach. So we consider a vertex to be finished when we return to it after finishing all its successors. In the previous algorithm, in the BFS approach, we actually uses a queue to implement it. In case of DFS algorithm, remember we will always use a stake to implement it. To get a more detailed view on how it works, let us consider an animation. Here is our animation example. We have given a graph and we are asked to traverse all the node by using DFS algorithm. Remember, we have to use backtrack algorithm and we have to go as deeper as possible. The first step is to select any arbitrary node from where we can actually start our algorithm. Let us consider that we have selected node A. Okay, and this is the example of a stake. And you remember, stake is like first in and first out, FIFO structure, or last in first out, or first in last out operation. The node at the top will be removed first. Let us see. During the execution, you will be able to clarify your concept. Suppose we have selected the node A. Mark node A, okay? Because we have to start from here. This is our starting point. Process the adjacent nodes to A. What are the directly connected nodes to A? They are C and E. To follow the sequence, we always consider the element that come first. That is C come before E. So we have to select C. And then you have to call the depth first search on the next node, which is C. We are done with that. But so we have to place A on this stake now. Okay, this is a recursive stake. And then you have to mark C as well. Now it's time to identify all the adjacent vertices of C. The first adjacent vertex is A, but A has already been marked, so we skip it. The next adjacent in a sequence is B. We apply the algorithm on node B, identified and placed it. Sorry. So we place C here once we identified the next node, and then we apply the algorithm on B, the depth first search algorithm. Now we have to mark B and identify all its adjacent elements. So here in this case, the adjacent elements are C and F. Process B and C, but we came to know that C has already been processed. Okay, so skip it. The next identified element adjacent to B is F, okay, which is not visited yet. So identify it, which means we have to place B on the stake now and come to the F node now. Do the same thing with this node F now. Adjacent elements to F are B, C, D, and E. First B. So B is already being identified, nothing to do. C, nothing to do. Now D. Okay, we have identified D, which is not visited yet, not identified node yet. We identified it, and then you have to place F on this stake and move to the next identified node, that is D. Now apply the algorithm on the node D. What are the adjacent nodes here? C and F. C already being identified, and C similarly is the case with F, which has already been identified. So now F is already been marked, being identified. So return to node F now. This is the big tricking part. Okay, as we do not have any other adjacent nodes, and we do not have all the adjacent nodes have already been identified, so it's time to big trick. Big trick, where we have to big trick from here. Stake will give you the answer. The element at the top of this stake is F. Stake is mostly used for recursion. So from where we come to this node? From F. So it's time to go back to F, and that is placed on the top of this stake. Go back, remove the element from the stake, that is F, which means back track to F by using recursion. Okay. Once you reach to F, now from here you can see that the adjacent nodes were B, C, and D. B, C, and D already being marked. What is not marked is E. Now it's time to proceed to E. Okay. So apply the algorithm on E. You have to place F on the stake because we are now moving to E. Now apply the algorithm on E on this node. Identify all the adjacent elements to E. The adjacent elements are A, C, and F. And all of these nodes are already being marked, identified, so we will skip. What we need to do now, we have to go bake tracking from where we come, from F. And you can see from the stick at the top we have F. So we have to bake track to node F. Okay, but node F has already been marked. And then we pop it from the stick, and then B pop up from the stick, and then C, and finally A pop up. Now, at the end, we have been identified a path like this, which is the deep first. I'm going to go faster. Yes, this is our final DFS tree, which you can actually use to process each and every vertex of this tree by using the deepest node first. So this is how we actually traverse the nodes of a graph by using the depth first algorithm approach. This was our last topic for this week. Thank you so much for watching the video. Next week we will come up with another topic of the algorithm analysis course. Till then, goodbye.